Uh, Sorry, Janab. Sorry for the interruptions. Unfortunately, power gets shut down. So that's why we could not continue. So let's start again. So where are we? So I was discussing that in chapter 5 we discussed primarily the bending moment and shearing force diagrams, right? So what is bending moment and shearing force diagrams, and what it tells us? It tells us that, for example, this is an example we took from the book, right? For example, we say that these are different type of loadings, right? There is some sort of torsion is there, torque is there, right? Not the torque, so sorry, this is a bending moment is there. These are basically the point loads. This is a uniformly distributed loads, and these are all creating sigmas and v's, so the normal stresses and the shear stresses, right? Shear stresses because of these shear forces v, and the normal stress is because of the moment. What it tells us? It tells us that from this shearing force bending moment diagram, we can calculate the load, that may be a shear force, or that may be a bending moment at any particular point. For example, at this point, I can calculate what is the moment and what is the shear force. For example, at this point, I can calculate what is by drawing a line from here to here, right? So it tells us that the assumption over here is, till now, no angular variation is there. Angle is basically 0 degree, right? So there is no angle involved. Everything is being applied either at the transverse section or at the 0 degree, right? But unfortunately, whenever loading comes, it is not necessarily that failure becomes along the plane. It can happen anywhere, right? And most of the time it happens at an angle. So what about the angles? How we can calculate the stresses because of any load conditions, like these, at any particular angle, right? So for that purpose we need to go for some angular transformations, right? And angular transformation that comes from the that is coming into this chapter 7, right? Fine. In chapter 1, if you remember, in chapter 1, we discussed normal stresses and shear stresses at an oblique plane. If you remember that we had this sort of and we applied a P over here, that is a tensile load, and then we cut at this section particular angle, and then we draw different stress conditions in terms of normal stresses as well as the shear stresses. And that was that if this angle is if this angle, for example, if I draw this in terms of, so it will be like this one, right? And this angle was somewhere was theta, if you remember. This was theta angle. Now what we did that, how this theta will be affecting the amount of normal as well as the shear stresses, right? And from there we calculated that sigma x prime, I mean, in certain directions, in this direction it was sigma, but now in this particular case it will be sigma prime because now angle is involved over there. That was p over a naught cos square theta, and tau x prime y prime was p over a naught sine theta cos theta. And if we go it, we can go for, like, if this is sigma, so sigma prime will be sigma cos k theta, and tau xy was tau sin theta cos theta, right? So this was tau xy was this. So now these are basically the angular transformation, because theta is there, sines are there, cosines are there, so we can calculate the amount of sigma normal stress as well as amount of shear stress that is being that is being that is being changed with respect to any particular angle theta, right? But this is only sigma x, this is only sigma x, right? If you remember, so now we stop this. So what we are going to do in this particular chapter, so now we are going in chapter 1 we were only focusing on the sigma x only. The rest of the all sigmas and all txy's were all shear stresses were zero, right? All shear stresses were in each direction was zero, right? But now we are going to see that what will happen if we go for a 3D state of stress or a general state of stress, right? So I stop sharing and now I'll share the book. Now we will go through directly to the book, right? This is chapter 7, so we'll start from chapter 7. Fine. So this is basically the general state of stress, right? This is the general state of stress, and in general state of stress we know, in general state of stress we know that we have total 6 stresses, 3 normal stresses and 3 shear stresses. And the normal stresses are basically the sigma x, sigma y, sigma z, likewise tau xy, tau xz, and tau zx, right? These are the 6 state of stresses, and xyz is the plane in which we are calculating, right? Right. Now if we transform this xyz plane into x dash y dash z dash plane like this one, right? So what will happen then? Like this one. So what will happen then? That then the sigma x, sigma y, sigma z will be transformed into sigma x prime, sigma y prime, sigma z prime. Likewise, tau xy, tau zx, and tau zy will be transformed into their prime values, right? So this is so there are total 6 stresses to define to total 6 stresses to define the 3D state of a stress or a general state of a stress in any particular. These are the stresses, not the loads. You cannot say that these are the loads. You cannot say that these are the moments, these are the forces, these are the torsions. No, these are the stresses, right? These are the internal phenomena. These are the reactions in response to the loads. And loads can be chapter 1, chapter 2, chapter 3, chapter 4, chapter 5. These are different type of the loads which are generating ultimately the type of the stresses. So now if we want to keep it a little bit simple, so then we can go that all are the zero except all stresses except x, sigma x, and sigma y's are there, right? And whenever we have sigma y and sigma z over there, so we will have some sort of sigma x, sigma y, and tau xy and tau zx over there. Oh, sorry, tau xy and tau yx is there. Since tau xy and tau yx are equal, so we can say that this is the only one quantity over there. So what we need is to define a planar stress, right? Or the 2D state of stress or the plane stress, because in plane we involve 2 planes, x or y, x and z, z and x, right? So this is xy plane. So these are the plane stresses. This is no more general state of stress. General state of stress in figure 7.1 in which we have the total 9 types of the sorry 6 types of the stresses. Now we have only 3 types of the stresses, right? Sigma x, sigma y, and tau yx, right? Fine. So if we draw this in a simpler format, so you can see that if we take this one, so this is the most common thing which we generally draw. This is sigma x, this is sigma y, this is tau xy, this is equal and opposite to these, right? So this is, so there is no angle involved. Now we want to involve some angle. If we cut this section along this side at any particular angle, then what will happen? This is what we want to see, right? Why we want to see this? Because most of the time failure does not occur in the plane. It most of the time it happens at any particular angle, right? So we want to know that in that particular angle, what will be the sigmas, and what will be the sigmas at those particular angles. And we want to determine that in the whole scenario, when there are multiple type of the loading, what will be sigma max and tau max value over there, right? So sigma x and normal values, and the shear stress value, maximum shear stress value, and normal maximum tau x value. So this is how, so we can calculate this by 2 methods. One method is the equation method, and second is the graphical method, right? So in this chapter 7 deals with both of these. Initially we will see this equation method, and then we will switch to the graphical method. This is a lot more easier than the equation method. So what we are, so our main objective in this chapter is that how we can calculate the maximum stress value using equations as well as a graphical method. And when I say graphical method, I refer to the Mohr circle. Mohr was a person who devised this method from the equations which we are going to drive in this particular section, right? So transformation of a plane stress value. Assumption is sigma y, sigma z is 0, resultingly tau xz, tau z, and yz equals to 0, and you will left with only sigma x and sigma y and tau xy value, right? And now we are transforming, this is the x value, this is x, and this is y. Now we are transforming this to the tau xy, x prime, and the y prime. This is the new coordinate axis that is existing at any particular angle theta from the reference of the x and y plane. So we are going to resolve these for this one, right? So what has happened over here? Let's see how to resolve this all stuff. So now, sorry. So this is the main stuff behind this, right? So when we cut it into the plane like this one, right? So this is delta A. This is theta angle exists between the x, y, and x prime, y prime axis, right? And this is delta A value. This area is delta A. If this is delta A and this is theta, so this is a right angle triangle. So delta A cos theta and delta A sin theta. This is the redefinition of base and the perpendicular in terms of the delta A, if delta is the hypotenuse for it, right? Now we add the sigmas over there. And when we add the sigmas, so by adding sigma over here, that will be obviously sigma x. So it will be a force. We know that sigma is F over A, and F is equal to sigma x delta A cos theta will be the force. So these are the forces which you can see over here, right? So then these are the forces sigma x prime delta a tau x prime y prime delta a, likewise sigma x tau x y as sigma y is other. Now what we are going to do, because this happens at the angle theta, so we need to resolve these as well, right? So what we will do, we will resolve this and this, right? So this is how you can resolve it. So this is positive, this is negative, right? Likewise, this is the positive shear and this is the positive shear. So they are in the same directions. Likewise, we will resolve this, we will resolve this, and we will resolve this. So we will resolve all this in the newer x plane and the x prime and the y prime planes. And then we will make sum of all the forces equal to 0 and sum of all the forces along y-axis equal to 0 along the x plane and the x prime plane and the y prime plane. That is the newer plane. So you can go for that. And then by the end of day, after solving all this, by solving all this, right? So solving this equation for the sigma x prime and the sigma tau x y prime will be like this one, right? Amazingly, if you look at this, that this is the same value we derived in chapter 1 when we are dealing only with the sigma x, right? So if we make sigma y and tau xy 0, so sigma x prime will be sigma x cos square theta, we derived in chapter 1 as well as we discussed today as well, just to revise the stuff, right? But since we are dealing with the sigma y as well as tau 2xy, so we will add all these, since sigma x cos square theta plus sigma y sin square theta, because between sigma x and sigma y 90 degrees phase shift exists. So if it is cos, it will be sine. If it would be sine, so it will be cos. And then since two tau xy values exist, one was tau xy, second was the tau yx. So 2 tau xy sine theta cos theta, right? So if we make this 0, if we make this 0, if we make this 0, so we left with only this part, which is the chapter 1. Again, if we make this 0, and if we make this 0, so you will left with only sigma x sine theta cos theta, which was again we have already seen in chapter 1 and today as well. Sorry, there was a mistake in the start when I did tau x prime y prime. So I mentioned there that was p over a naught was the tau xy. That should not be tau xy, that should be sigma x, right? So, but these are not 7.1 and 7.2 are not the main equations which we are dealing with, right? Then we use these trigonometric identities like this one and this one and this one and this one, and incorporate into the 7.1 and 7.2, and then we end up with this sigma x prime value and sigma x prime value, as well as below sigma tau x5 prime values. These are two important equations, 7.5, 7.6, and 7.7. These are the three values which can be used for the 2D state of a stress or a plane stress to calculate sigmas as well as taus at any particular angle. At any particular angle, right? So you put the value of theta over there, whatsoever that is, right? And then you can calculate that what will be the sigma as well as tau in that particular angle, right? So this is how we can calculate it, right? So from here, if we go onward, now if we want to calculate maximum stress value, so how we will calculate that, right? So if I say one thing before going into the details of this is basically the circle, right? So what is the equation of a circle? You tell me. What is the equation of the circle? Anybody? Can you tell me? This is x square plus y square equals to r square, right? R is basically the radius of the circle, right? This is R. And what happens if I shift this angle, shift this circle at any position A? This is x and this is y, right? Again, this is x and this is y. So now what will be the equation? X minus a whole square plus y square equals to r square, right? This will be the equation of a shifted circle. Now what if I replace this x with sigma and this y with tau? So it will be sigma minus a plus tau equals to r square. So what Bohr did? Bohr did an amazing thing. I don't know how he did that. Might be sleeping in the night and he saw some dream, and so he solved this, that the equation 7.5, 7.6 and 7.7, somehow he related it with the circle. And how he did that? So let's see how he did that. So let's go upstairs. Let's start from this equation 7.5. He said that this is sigma x plus sigma y over 2 is sigma average. And then he brought the sigma average, so it becomes sigma x prime minus sigma average equals to whole of this expression, Then he took square of that and he took square of that. Further, he took square of this equation and he took square of this equation and solve it. What he did? He added this sigma x minus sigma average plus tau xy, right? And equals to, by doing all the mathematics and doing all the stuff, he concluded that this remaining stuff is equals to r. So what he did, he said sigma x prime minus sigma average square plus tau x prime y prime square equals to r square. So this is what it is. This is the equation of a circle we just saw. Instead of a, we are now having sigma average, rest is r square. So if what he take a plus b whole square and again a plus b whole square over here, and then he added and some terms, because this will be cos square 2 theta, sin square 2 theta, sin square 2 theta, cos square 2 theta, and 2 into cos 2 theta, sin 2 theta, and 2 sin theta, cos 2 theta with some constants before that. Cos square 2 theta and sin square 2 theta is equal to 1. Sin square 2 theta and cos square 2 theta again becomes equals to 1. So sigma x minus y over 2 whole square plus tau xy whole square under root was equals to r value somewhere, I think. And rest the third, because it will be total 6 terms will be there. a square plus b square plus 2ab, a square plus b square minus plus 2ab. So it will be by the end of day, it all will be the two ab's terms will be cancelled out, and you will left with only a square plus b square values, and a square plus b square values will be cos square 2 theta sin square theta 2 will 1. So sine and cos will be vanished from the system. So by the end of day, you would become sigma x plus sigma y over 2 square plus tau xy under root, and sigma average was sigma x plus sigma y over 2, and this is the whole equation of this one, right? So what he did, so this is now circle, this is now circle, this was our a, now this has become sigma average, and he draw the circle, right? So these are the 2 points, point A and point B. Obviously this is sigma max value, this is sigma min value, and sigma average will be sigma max plus sigma min divided by 2, right? And sigma max will be over here, right? And then you keep on changing at any particular angle here, 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 these will be sigma x prime and tau xy prime, right? Right? So this is the circle. So at any particular location, at any particular angle, you can calculate sigmas, and this is sigma max, and this is tau max value, right? And one finding is that when sigma is maximum, tau is 0. Again, chapter 1. And when tau is maximum, sigma is not 0. Sigma has some value. And this is the radius. And radius we know sigma x minus sigma y over 2 plus tau xy whole square. We can calculate because this is the hypotenuse for this right angle triangle. Right? So sigma max and tau max can be calculated using this Mohr circle. When we will go for the combined load stresses, so we will see what happens with these stresses, and from there we will evaluate that what will be the maximum stress and what will be the maximum shear stress as well as maximum normal stress value. And then we will say as an engineer that this design is safe if your allowable sigmas, because of those particular combined loading that is being applied on the beam, is if lesser than sigma values and the TOS values, so you are safe, otherwise you are not safe. So the prime objective of this Mohr circle is to calculate maximum sigma values and maximum tau values so that you can compare it with the allowable limits. And if your allowable limits is below these values, so you are safe, otherwise you are not safe. So your work is not done when you calculate only sigmas or any particular angle using the equations, right? So this is the very easiest way, because you can calculate the maximum sigmas using the equations, but then you need lots of computation over there, because you might go between one you might find a particular value, maximum value between 40 degree and 41 degree. Then what will happen? There might be some there may be some maximum which happens between at 40.1 or 40.2, 40.3. So then you have to calculate again, and that is an iterative process by which you will calculate the sigma max using the equation. Instead of that, this Mohr circle directly gives you the values. So this is sigma A, sigma X, sigma Y, sigma minimum value, sigma maximum value, right? And from there you can calculate the tau maximum value, right? And from there you can decide that if your allowable limit is lesser than these values, so you can easily say that your design is safe. So this is all about the Mohr circle. In next lecture, we will go for some mathematical application, numericals of all these, and let's see if there is some slide shares in equation part, right? So these are chapter 7. So this is the revision. Sigma p over a naught cos square theta, tau p over a naught sin theta cos theta. And when sigma is maximum, tau is 0. And when tau is maximum, sigma is not necessarily equals to 0, right? Then this is the whole bunch of the stuff we have already done. This is what we did with this stuff, how these equations are equal to a circle. And then we can calculate that sigma maximum value and sigma minimum value. Sigma A and sigma B will be the stresses, right? And then we will see how to draw this circle and how we can go for it. So sigma average will be sigma x plus sigma y over 2. R will be this. Sigma max will be sigma average plus radius, whereas sigma minimum will be sigma average minus r. So to calculate sigma max and sigma minimum, you need to calculate this equation, right? And sigma tan to theta p tan to calculate the angle at which these will happen. So that will be tau xy over sigma x minus sigma y, and 2 will go up, and this will be 2 tau xy sigma x minus sigma y. And then you can go accordingly for the rest of the stuff, right? So these are basically, so these sigmas are called the principal stresses, right? Principal stresses occurs on the principal plane of stress with zero shearing. So this is your principal plane of stress. This is your principal plane of stress. When tau is equal to 0, so this is called principal planes of stresses. And principal stresses are sigma max value and the sigma min value. And obviously, your tau max will be equal to the radius of this circle. Whatever the radius is, that will be your tau max value. So you have to see that the total cumulative amount of the tau because of the torsion as well as because of the shear force V, chapter 6 and chapter 3, should not be greater than this tau xy value. And chapter 2 and chapter 4, bending moment and the axial forces generally creates the normal stresses. So cumulative effect of the normal stresses should not be greater than the sigma max value. If that is done, so you are safe, right? So your allowable stresses, if lesser than sigma maximum value and tau max values, so you are safe, otherwise you are not safe. So here we end our chapter, sorry, not the chapter, this lecture. And in next part we will go for the mathematical stuff, how to draw the circle and how to calculate different values. Thank you very much.